Very good. Sprintathon, exactly. Okay, so our next topic is support vector machines. Let me get my notes. So we talked about a few different classifiers so far. We had a logistic regression classifier, we had a k-nearest neighbors and decision tree classifier. And we're going to look at one more classifier that's going to be especially useful, mainly actually because it leads us to neural networks in a future week. So this is kind of very important for the development of the course. So we're going to return to our binary classification problem. Our class labels are going to be -1 and 1. Right? So we have a bunch of training samples. Each has p features. So each training sample is a vector of length p, and each has a class label of -1 or 1. And we know that the problem is considered perfectly linearly separable if we can define some hyperplane such that all samples in one class are on the positive side, all samples on the other class are on the negative side. Okay. And we know that the separating hyperplane has a property that, okay, so let's draw it. Okay, so imagine you have the separating hyperplane. It's defined by W0 plus W1 x1 plus W2 x2 equals to 0. Okay. And we know that all samples on the positive side, meaning where this quantity is greater than 0, have label +1. All samples on the negative side, meaning this quantity is less than 0, have label -1. Okay. And since our class labels are -1 and +1, you can then kind of rewrite this so that the separating hyperplane has the characteristic that the label times this quantity is always greater than 0. Okay. And then we know we can classify a new sample using the sign of this quantity. And the magnitude of this quantity tells us how far we are from the hyperplane. So we know that, let's say, a point that's very far from the hyperplane will have a greater value for this than a point that's very close to the hyperplane. So that gives us some measure of our confidence. And then we also said that if you have one separating hyperplane, you have many potential separating hyperplanes, which leads us to the question of which separating hyperplane is best. Now, when we looked at logistic regression, we found the maximum likelihood classifier. So that was a hyperplane that maximizes the probability of these particular observations. Okay. For this week, we're going to look at what's called a maximal margin classifier. Now, what does that mean? Okay, so let's say for any candidate line, let's say this candidate hyperplane, I'm going to compute the perpendicular distance. This perpendicular, sort of. So the perpendicular distance to every possible point. Okay. So something like this. Something like this, but I'm going to compute the distance for every single point in the entire data. Now, of all of these perpendicular distances, I'm going to take the smallest one. Okay. And I'm going to think of this as being actually half of the margin. Okay. What does that mean? It means that I could take kind of this slab. Let's make this a dotted one. So I can, let's say, draw a rectangle like this. That's kind of empty in the middle. And we're going to choose a hyperplane that maximizes how wide this slab is. So it maximizes a margin. And then the middle of that rectangle will be the decision boundary. So we're going to find the distance from every point to every candidate hyperplane. And then the smallest of those is considered the margin, or half the margin, actually. And then we're going to choose a hyperplane that maximizes the margin. So this is called the maximal margin classifier. Now we have a special name for the points that are on the boundaries. Okay, so these points here. Okay, these points are known as support vectors. Why are they known as support vectors? They're known as support vectors because these points alone determine where the hyperplane lies. If I move a point that's not a support vector, like if I move this point, has no effect whatsoever on the hyperplane. But if I move a point that is a support vector, let's say if I move this point, now I end up moving the entire hyperplane. So they're called support vectors because they support the hyperplane in the sense that the hyperplane's position depends only on those points. Now, how do we actually build this maximal margin classifier? So to construct this classifier, we're going to set it up as a constrained optimization problem where we have an objective and we have one or more constraints. What do you think the objective and the constraints are? So when I say an objective and constraints, I mean objective is going to be, let's say, minimize or maximize some function. And constraints are going to be subject to, for example, g of x greater than or equal to 0. That's just an example. Okay. Now, for this particular problem, what do you think the objective and the constraints are going to be? Well, the objective has to do with the margin. I'm not sure what minimum difference between margins means. So we said the maximal margin hyperplane is the one that has the largest margin. So let's just say we want to maximize the margin. And what is that subject to? So let's say we have this margin. It's wider. Does that make it better? Okay, so it's not better because then we have points inside the margin. We might have a hyperplane that ends up incorrectly classifying samples. So we want to maximize the margin subject to all points on the correct side of the margin. So every point should be outside the margin and it should be on the correct side of the margin. So we don't want, let's say, a point outside the margin here. That's not on the correct side. So this is the optimization problem we want to solve. Okay. So we could express that actually like this. So we're maximizing the margin. I'm going to use gamma to denote the margin, where gamma is this total width. Okay, so that's the margin. I want to maximize the margin subject to these two conditions. What do these two conditions say? Well, one condition is on the, let's say, on the L2 norm, so kind of the size of the weights. Okay. We're saying the weights should be a unit vector. Now, remember that if we have a separating hyperplane, right, any scaled version of it is also the same separating hyperplane. Right? So we could add, let's say, kw0 plus kw1 plus kw2. It's the same line. Right? So this constraint doesn't actually affect the position of the hyperplane. What this constraint actually does is it makes the second constraint works. So if we apply this constraint, and you could convince yourself of this later, if the weights have unit vector, then the distance of a particular point from the hyperplane is going to be equal to so this distance is going to be equal to W0 plus W1 x1 plus W2 x2. So enforcing, let's say, the unit vector constraint just has the effect of making this true, that this quantity now defines the distance between a point and the hyperplane. So we have the distance between the point and a hyperplane. Now, the y variable, which is the sign, the class, defines which side of the hyperplane it's on. So we want a positive point. Okay, so a positive sample will have this positive distance from the hyperplane. So it will go in this direction, which is a positive direction. A negative sample will go in the other direction. And so this constraint says that the distance from a point to the hyperplane should be at least gamma. And of course, it should be on the correct side. So this is the objective function for the maximal margin classifier. We're maximizing the margin subject to the condition that every sample should be outside of the margin and it should be correctly classified. Okay, so every observation should be on the right side of the margin and it should be at least gamma distance away from the hyperplane. And we want to maximize gamma. Now, what happens if the data is not linearly separable? Can we solve this problem? Let's say I put this point over here. If we put this point over here, there is not going to be any solution to the problem. Okay, so there is no gamma that's set or weights that satisfy the problem. So that's one problem with the maximal margin classifier. The second problem is actually that it's very much not robust. Okay, what do I mean by not robust? So I'm not going to attempt to draw this out right now, but you could see, for example, so here's an example with this gray rectangle showing the margin. And if I add just like one new point, I can end up changing the entire hyperplane a lot. So one new observation can shift the hyperplane a lot, when it's really possible that this just happens to be an unusually noisy point. And maybe the first hyperplane was better. So that leads us to the support vector classifier, which is an extension of the maximal margin classifier to the non-separable case. Okay. For the support vector classifier, we're going to use a hyperplane that almost separates the data. So this is what's known as a soft margin. Okay. So let's say I have this here, but I have some points that might be, let's say, in the margin here. With a support vector classifier, that's actually allowed. I might have some points that are, let's say, in the margin, but on the correct side of the hyperplane. I might have a point like this one, which is in the margin, but on the incorrect side of the hyperplane. That's all allowed, subject to some constraints. Let's define the support vector classifier. So it's very similar to the previous classifier, the maximal margin classifier. But now, instead of making the points be gamma distance away from the hyperplane, now I say they have to be gamma times 1 minus epsilon, where I have some epsilon per point. Okay. And I'm also enforcing that the sum of all the epsilons has to be less than some constant. What does that mean? Okay. Well, let's say I have a point that's over the margin, but not over the hyperplane. Okay, so this point, for example. For this point, we have, let's see, copy that. For this point, we have an epsilon greater than 0, which means that the distance so the distance from this point, the distance of this point from the hyperplane is actually not greater than gamma. because we have a non-zero epsilon, so an epsilon greater than 0. So the difference between the distance from that point to the hyperplane is gamma times something less than 1, right? Something between 0 and 1. So this defines, let's say, how far the point is from the hyperplane. What about this point over here? For this point over here, we'll have epsilon equals 0. Okay. This point is at least gamma away from the hyperplane. And by the way, gamma is just this distance here. So this point is at least gamma away from the hyperplane. So we can let epsilon be 0 for that point, and it satisfies that constraint. This point has epsilon greater than 0 away from the hyperplane. Same deal for this point. I'm actually, sorry. So this point is also, let's say, between the margin and the hyperplane. And then we also have this point here, which is even farther from the margin. And for that point, epsilon is actually greater than 1. Okay. So for this point, we have this quantity ends up being that this point is more than gamma away from the edge of the margin. And it's actually on the wrong side of the hyperplane. So we have these epsilon i's where the greater the epsilon I, the farther away the point is from the edge of the margin, but in the wrong direction. Now we have some constraint k. What does k tell us? K tells us that if you add up all of these distances, actually we're going to add up the square of all the distances. The result should be not more than k. So I add up all these distances, and the result cannot be more than k. So k is like a budget that tells us how many points over the edge of the margin we can tolerate, or how far over the margin they can be. Okay, any questions? Okay. For the support vector classifier, the points that affect the classifier are those that are on the margin or over the margin. So we have some more support vectors. So in this case, this is a support vector because it's on the margin. But these points which violate the margin are also support vectors because moving those points also affects that overall optimization problem. Okay. What happens as k changes? So if I increase k, will the margin get wider or smaller? If I increase k, I have more budget for points over the margin, right? Which means points are allowed to be farther over the margin. So in that case, my margin will actually get bigger. If I make k smaller, then I have less budget to tolerate points over the margin. So then my margin will get smaller. Okay. So k actually controls the bias variance trade-off. Okay. When you have many support vectors, then any individual support vector is not going to affect the overall hyperplane as much. So if you have many support vectors, the variance is low. On the other hand, the bias may be high. Okay, so if this k is large, you have many support vectors and a wide margin, but the variance may be, the bias might be high. When k is small, you have fewer support vectors, but you have more variance, but potentially lower bias. Okay. Now, when we gave our recipe for, let's say, what a supervised learning algorithm looks like, we said that we'll always end up training to minimize some loss function. So we described an optimization problem here, but we didn't actually say what loss function it minimizes. It turns out the loss function that this minimizes is called the hinge loss function. And it looks like this. So this expression here is called the hinge loss, where the loss is 0 if a point is not over the margin. And then we have increasing contribution to the loss function for every point that's over the margin. So each of these points that are not over the margin have a loss of 0 according to the hinge loss. And each of the points that violate the margin have some non-zero loss in proportion to how far they are over the margin. This is in contrast to our logistic regression. For the logistic regression, we had gradually increasing loss as you move farther from the hyperplane. Here, we have loss only inside the margin, but if you're outside of the margin, you have no loss at all. Okay, there's a question in chat. Why is there potentially bias when K is smaller? So when K is smaller, you actually have a lower bias usually. Okay. So you can think of it as the more support vectors, the more smooth the result is, and a smoothed result tends to have higher bias. But the bias will always depend on what the actual true function is. So depending on the true function, you might not necessarily have higher bias, but we'll look at that more when we look at some examples on Thursday. Okay, so up until now, I kind of gave the overall concept of the support vector classifier. And now I'm going to get into how you actually solve it. All right. So this is going to get very mathy. If you haven't learned constrained optimization at all, I'm going to try to give the kind of overall flavor. So it'll be a little bit hand wavy in that sense. But we're going to walk through the process of solving that optimization problem. Okay. We've previously described some, general purpose methods for solving a convex optimization problem. So for a general convex optimization problem that's unconstrained, we can take a gradient of the, let's say, function we want to minimize, set it to 0, and solve. Or we can use something like gradient descent to numerically find a solution. What do you do if you have some function with some constraints like this one? Okay. So this was our original problem formulation for the support vector classifier. We want to maximize the margin subject to some constraints where this constraint basically just clarifies this constraint, okay, which says that every point should be on the correct side of the hyperplane, except for some points where epsilon is non-zero. And for the points where epsilon is non-zero, we have this overall budget K. Now we know that any scaled version of the hyperplane is the same version. Okay. So we have the scaling parameter here. We're going to adjust it so it's a little more convenient. We're going to say this quantity should be inversely proportional to the margin. What does that do for us? Well, it helps in two ways. First of all, we can get rid of this, which is not particularly helpful. We're just going to do that anyways. But what's really helpful is that we get rid of this. And now, instead of maximizing the margin, just going to remove this, we just need to minimize this quantity. Okay? So we're just going to define this quantity as being inversely proportional to the margin. And now, since we want the margin to be maximized, we want this quantity to be minimized. So that gets us to this expression right here, this equivalent problem formulation. So now we're trying to minimize, let's say, the L2 norm of the weights, subject to this condition. So we're still, enforcing the whole over the margin thing and budget. It just looks a little bit different because now we're using the norm of the weights to define the size of the margin. So we have this equivalent problem now. And we're going to make it further simplify it by moving this part into the objective function. Okay. So we're enforcing that the sum of the epsilon should be less than some constant. We're going to move this constraint into the objective function by saying some other constant times the sum of epsilons is in the objective. So by minimizing this overall objective, we're enforcing that constraint. So that leads us to this equivalent form. Now, in order to continue this solution, we're going to give a little bit of background on constrained optimization. What we have here is an objective function that looks like, let's say, f of x, subject to some constraints that say, let's say, g of x greater than or equal to 0. And we have, let's say, some constraints up to g of p. What do I mean up to g of p? Well, this has to hold for every I and n. So for every sample, we need epsilon greater than or equal to 0. So that means we have actually n constraints because of this term. And similarly, we have n constraints because of this term. So we actually have 2 n constraints, where n is the number of samples. And they still actually fit the requirement of, let me erase that. They still are in the form g of x less than or equal to 0. You just need to, let's say, do a little bit of algebra. So then you could say negative epsilon I has to be less than or equal to 0. But they're still all in this general form. And by the way, when I say f of x here, by x, I just mean whatever quantity we're optimizing over. So here it's, let's say, really a function of the weights. Okay. So we have this optimization problem that's in the general form of minimize f of x subject to g of x less than or equal to 0. And we can have many such g of x constraints. So this is a general form of a constrained optimization problem. Now I'm going to illustrate this problem, and I kind of drew something for this in advance. So imagine you're trying to minimize some function of x. Okay, so here are some contours that show f of x, and it's minimized at some point in the middle. Now I want to add a constraint. Okay, so I'm going to add a constraint on g of x. So I'm going to add a constraint that g of x has to be less than or equal to 0. And let's say that this square defines a region where g of x is less than or equal to 0. Okay. This square here is what's called the feasible set. So my solution has to be somewhere in the square. Is this a valid solution now? Okay, so this star is not a valid solution because it's not inside the feasible set. What about this star? Would this star be a good solution? This star is inside the feasible set, but it doesn't minimize f of x. So what are the conditions for constrained optimization? I want to find the point that satisfies the constraint, so is in the feasible set, but among all the points in the feasible set, it should be the one that minimizes f of x. So in this example, it's going to be this point right here. Is there any other solution to this optimization problem, or is this solution unique? Okay, so this is a unique solution. I'm looking from all the points in the feasible set, which is the one that minimizes f of x. So that's the general idea behind a constrained optimization problem. Now to solve it, we form something called the Lagrangian. Okay, so Lagrangian is basically, we take each of our constraints. For each constraint, we introduce a new optimization variable, That's called the Lagrange multiplier. And so we form the Lagrangian as, let's say, the original objective plus the Lagrangian times a constraint for each constraint. Okay, so here, for example, I have m constraints. This quantity is called the Lagrangian. Now, if you look back here, right? So remember we had, let's say this was an optimal solution towards to the objective minimizing. And now we have this alternative expression as a Lagrangian. This term, so these terms, let's say the Lagrangian times the feasible times the constraint, pulls a solution towards the feasible set. So now if I try to, let's say, solve this problem where I'm minimizing this instead of the original objective, you could see that the Lagrange multipliers pull towards the feasible set, where the greater the Lagrange multiplier value, so the greater the value of lambda, the more strongly I'm pulled towards here. Okay. Now to solve this, we then solve a joint optimization problem. Okay. The joint optimization problem looks like this. Inside the optimization problem, we have the Lagrangian, so f of x plus lambda g of x. And if you have many constraints, you would have lambda 1, g1 of x plus lambda 2, g2 of x, and so on. And the lambdas must be greater than or equal to 0. And we try to first maximize this quantity by maximizing over lambda. And then we minimize this quantity by minimizing over x. What does that mean? Okay, so let's look at two examples. Let's say I have this, okay? So the contours show f of x, and this rectangle shows the feasible set. Now, I want to maximize this quantity by setting lambda. Okay. What is g of x? So we know that this point here, let's say I pick this point. I want to see whether it's optimized or whether I can improve it. Okay. What do we know about the value of g of x star? We don't know the exact value of g of x star, but we know that it's less than or equal to 0 because it's inside the feasible set. If this quantity here is negative, what value of lambda should I pick to maximize this overall function? Okay, so if g of x is negative, meaning the x we picked is inside the feasible set, then I'm going to select lambda equals 0 in order to maximize this function. That's called an inactive constraint. So when the solution is inside the feasible set, the constraint is not active, and I'm going to set lambda equal to 0. Now, what happens if I have this point here? Okay. And okay, let's say I'm evaluating this x over here. Actually, sorry, I'm evaluating this x over here. What do I know about g of x star? Okay, so this is the feasible set where g of x is less than 0. And I'm evaluating this. So x star is not in the feasible set, which means that g of x star is greater than 0. If g of x is greater than 0, what value of lambda should I pick in order to maximize this overall function? Okay, so this is greater than 0. To maximize this, I want lambda to go to infinity, right? So to maximize the overall function, I'm going to have lambda go to infinity. Now, suppose I have lambda going to infinity, but then I need to minimize the overall function with respect to x. If I have to minimize the overall function with respect to x, what does that force me to do? Well, it forces me to move the value of x that I'm considering so that g of x is smaller. Which direction am I going to go in to make g of x smaller? That means I need to move towards a feasible set, because a feasible set is where g of x is less than or equal to 0. So if the constraint is active, right, which means lambda is going to be greater than 0, then I need to move x in order to make g of x smaller in order to minimize the overall function. So that's how this joint optimization over x and lambda works. Okay. So I solve this optimization in the usual way. I take the partial derivative of this with respect to every argument, set it to 0, find the solution. But I have this pull between f of x and lambda g of x that ends up making the constraint tight. Okay. So I end up with a solution where either g of x is equal to 0, so I'm at the edge here, and lambda is non-zero, or the constraint is not active, and then lambda equals 0. Okay, so this is how the constraint optimization works. Okay, so let's go back to our support vector classifier formulation. But first, I'm just going to mention one other thing. Okay. So that if we solve this optimization problem, okay, the solution to this optimization problem, let's say the point in the Lagrangian, that's, let's say, okay, the solution to the original optimization problem, so the optimal point of this function is going to be a saddle point on this function. So we can find it the same way by taking the partial derivative and setting it to 0. And also for certain types of problems, which includes our support vector classifier problem, we can alternatively solve a different problem called the dual problem, where we change the order here. So here I change the order so that the minimization is on the inside and the maximization is on the outside. Under some circumstances, that ends up being easier to solve. And for problems that have what's known as a strong duality, the solution to one is the same as the solution to the other. Okay, so now that we have that bit of background on constrained optimization, we'll go back to our support vector classifier problem. So we had, let's see, we had this expression here. Okay. And we're going to rewrite this expression. We're going to take the Lagrangian. So all of these constraints are going to be moved into the objective function, but with some Lagrange multipliers. So we end up with this formulation, which is the Lagrangian primal formulation. So we're minimizing over the weights and maximizing over the Lagrange multipliers. Okay. And each of those constraints was moved into the objective function with Lagrange multipliers alpha and mu. Okay. Now we're going to make another slight change. So we said this problem has strong duality, so we can alternatively solve the dual problem, which is the same thing, just switching the order of the min and the max. Now, it turns out that the dual problem is not too difficult to solve. If I take the derivative of this, set it to 0, solve for, let's say, these weights and epsilons, and then plug in the result back into this formulation, okay, so then I end up with this. Okay. So I've done the minimization part. Okay, take the derivative of this with respect to the variables I'm minimizing over and solve, then plug those solutions back in. Now I just have to maximize this expression, which turns out to be not very difficult to solve. Okay. And the optimal coefficients, so the optimal weights for every weight except the first one, is going to turn out to be this expression here, okay, where these alpha terms come from the solution to the dual problem. And the alphas are going to be greater than 0 only when the constraint is active. Okay, what does that mean? So this is a constraint that says we have to be on the correct side of the margin, or at least with an epsilon if it's subject to our epsilon budget. So for all of the points that are easily classified far from the margin on the right side, on the correct side, the constraint is not active and alpha will be 0. Alpha is non-zero only for the support vectors. So when we use this expression to find the optimal weights, actually all of these alphas, we have an alpha per sample, but they're non-zero only for the support vectors. So we take the sum over all the samples, but really we're only taking the sum over the support vectors. Okay. And similarly, we can solve for the intercept term, W0. And so this turns out to be a relatively easy solution, okay? Because, well, in the primal problem, so this was a primal problem. In the primal problem, in the, let's say, outer problem, you need to, let's say, solve over however many coefficients there are. So let's say P is a dimensionality. In the dual problem, you need to solve over, let's say, however many samples there are, because you have one alpha mu per sample. But it turns out that these are non-zero except for support vectors. So it ends up being relatively more efficient to solve the dual problems because there are only as many non-zero dual variables as there are support vectors. And there is another reason to solve the dual problem called the kernel trick, which we'll discuss next week. I just want to leave you with one thought about how to interpret this. So there's a kind of correlation interpretation of the support vector machine, which is as follows. Suppose you have some new sample to classify. So you compute this, okay? So W0 plus this expression, right, where this comes from, those weights we discussed. You could see that this measures, let's say, a weighted inner product of the original point of the support vectors and the test point. Okay. So this here is the new point we want to classify. And this point takes the dot product of the new point and each of the support vectors. And it's actually a weighted dot product according to alpha. We know alpha is 0 for all non-support vectors. So this entire sum is really only over the support vectors. The dot product is like a kind of correlation. It's most similar to, it's more similar. The dot product is greater if these two samples are similar. So you can think of this as kind of a correlation interpretation, where for each new sample, your prediction is going to be a weighted average of the labels. Okay, so remember Y is a label, alpha is a weight. You're taking the weighted average of the labels of all the support vectors, where the weight is according to both alpha and how similar the support vector is to your new sample. So a more similar support vector counts more in your overall classification than a less similar support vector. Also, your alpha determines, let's say, which points are support vectors. So it's like a weighted average of labels for support vectors. Why it doesn't make sense to use the support vectors for classification? Well, remember that the support vectors are the points that are on the margin or violate the margin. Okay. Are these points more likely to be kind of difficult points to classify or easy points to classify? Okay, so difficult. So when you're, let's say, classifying a new point, well, you're taking special care to make sure it's correct with respect to most difficult classifications. And we'll look at that also on Thursday. Okay, I'm going to leave you here because it's 11 o'clock. Are there any questions? I know it's a lot. You might have more questions later, and of course, you're welcome to post those on Ed. But are there any questions right now? All right, very good. I will see you all on Thursday.